Oh, thank you. And again, I apologize for the mix-up.
Oh, please. These time zones are always a mess. I got it right only because I checked it twice.
Okay, I think, let me see. Yeah, we're live then. Okay. Hello, everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today, we have the honor of having Dr. Claudia Maraston, a professor at the University of Portsmouth. Dr. Maraston is an expert in the modeling of the spectrophotometric and mass properties of galaxies. These so-called stellar population models find ubiquitous applications in astrophysics and cosmology. In particular, they are the tool to study galaxy formation and evolution, both theoretically and by interpreting data. Her research interests are in stellar population modeling, galaxy evolution modeling, high redshift galaxies, and globular clusters. Dr. Maraston, thank you so much for being so kind and having accepted to give us a webinar talk today on such an interesting topic. The floor is yours.
Thank you very much to you for this kind invitation, and I hope you will enjoy the talk. So, as I've been just introduced, I will discuss a topic that has been crucial in astrophysics since the 70s, which has been called evolutionary population synthesis, and I will have the opportunity to explain exactly what the naming means. So the broader context is the understanding of galaxy formation and evolution on a cosmic timescales. You see to the right the well-known biography of the universe, where indeed the time scales without the light emission encompasses the very first times of the universe for a time scale that is not longer than 400,000 years. And after a short period called the Dark Ages that is being currently probed by the James Webb Space Telescope, we certainly start at some point having the first stars which then get together to form the first galaxies. And for the rest of the 12 billion years and over of cosmic time, it is all about galaxy formation and evolution. But this is a very complicated process. As we know, I learned it as a student that it was complicated. And although a lot of progress has been done, there are a few processes that are really difficult to probe from first principle. For example, the conversion of gas into stars, which is something that includes cooling, complicated cooling function and metallicity, and also especially gas plasma dynamics. We do not have one equation that can satisfactorily describe for any kind of astrophysical situation how a gas cloud converts into stars. And related to the above, we have the problem of describing feedback from stars, which we know it certainly existed in form of ultraviolet emission from the most massive stars, and which came about over the past few decades also from massive black holes. We have then the problem that if we wanted to model structure on a cosmological timescales, we have the problem of describing the growth of mass due to dark matter merging, and also which came about to be popular just in the past few years. It is also complicated to stop star formation, considering that the dying stars release gas on a secular timescale, which in principle could also be, and it is in some situations, reused for new stars formation. And this is called quenching or starvation. So all in all, we have a lot of problems. So how do we want to tackle this problem? And before passing to that, first of all, now it's 2022, I can use this beautiful image from the James Webb Space Telescope, projecting us into cosmic time, showing galaxies of the various types at different redshift for cosmic distances. What quantities do we need to know in order to actually assess galaxy formation and evolution? Well, we need the distance from the galaxies, the redshift, the age and the formation epoch of galaxies, the star formation history, which will also allow us to make prediction on how this galaxy would evolve into the future, the detailed chemical composition, which again has an impact on the structure of the galaxy overall, and also formation of conditions suitable for life, to take it to the extreme. The stellar mass, which is one of the crucial quantity to trace the growth of structure in a cosmological model, and related to this, the remnant mass, which we know now it has always been important, but since a few years, it became at the center of the detection of gravitational waves. And the dark matter, which indeed can only be devised by having a good knowledge of the previous two mass components. So how do we go about deriving these quantities for galaxies across the cosmic time? Well, it all relies on modeling the spectra. In this plot, I use one of the Sloan Digital Sky Survey high signal to noise the spectra just for illustration, published in Parikh et al. You see flux versus wavelengths in the rest frame. And this is just a show off of the optical suite of lines that in fact we have at disposal to determine redshift, but also especially in this portion to determine accurate chemical composition, detail abundance ratios, various elements. Here we have iron, but also alpha element like magnesium. We have sodium, we have calcium, we have element sensitive to carbon. So the art is, are we able to model the spectra? Now, what I will be telling you in this talk will be first, an overview on the stellar population model, on the technique and how it developed over history. And then I will, of course, to make the seminar timely, describe our latest effort, which is based on utilizing 60,000 spectra, the largest number used so far in population synthesis, which we gather from the Sloan Digital Sky Survey Spectral Library. I will then discuss applications of this model that have a direct impact on galaxy evolution across cosmic time, interpreting observation and predicting galaxy evolution. So the story of trying to model and observe the spectra started back in the 70s, as I said. And the first effort is something that was called optimized population synthesis. And I will clarify immediately what optimized means, but you will recognize Eduardo Bica, who is a Brazilian astronomer who was one of the actors, in fact, in this fundamental first attempt to model the spectrum. Sandy Faber in her thesis 1972, and Bob O'Connell in the United States in 1981. So what it is based on the knowledge that an observed spectrum will certainly be a combination, linear possibly, of spectra of individual stars in various evolutionary phases, which we can tune by multiplying them with the open coefficient, with the free to tune coefficient, which will give us the weight of the given spectrum to the total. So essentially, optimized population synthesis entails combining empirical spectra with arbitrary weights. That's very important. The weights are arbitrary, and one can indeed find a fantastic match to an observed spectrum, in most cases actually to a portion of it, because as you can imagine, there is galaxy evolution. The real conundrum in this type of models, which this was very well known to the authors, I'm not saying something that they didn't know, is that obviously by being an ad hoc fit to a spectra to give a snapshot in time, it is not a model and it cannot make prediction for how that the given galaxy came about to be at that time, or how it can be evolved in time. However, it is still used in data analysis pipelines, including the Sloan, for example. You see a couple of citations, when the interest is mostly to have a very accurate modeling of certain absorption lines, for example, for kinematic studies. So the clue is to determine velocities independently of the fact that whether the galaxy realization that you would achieve is actually feasible. Another domain in which optimized population synthesis still used actually very much, and this is actual based on galaxies from the James Webb Space Telescope, is to obtain redshift. And this is made, for example, by a code called EASY, where an arbitrary combination of templates of disparate age and chemical composition are combined to optimize the photometric redshift accuracy, and that again not necessarily will correspond to physical parameter for galaxies. But there was another approach that was put forward in the early 70s by Beatrice Tinsley, which you see here to the left, which wanted to go a step forward and try to challenge what was the knowledge of stellar evolution at the time, and to try to push this type of modeled spectra to actually be able to make prediction suitable for astrophysics and cosmology, so prediction along the cosmic time. And this is how this population synthesis is called. It is actually called evolutionary population synthesis instead of optimized, exactly because the scope is to exploit fully the laws of stellar evolution that at the time were being actually calculated and applied to a wider range of stellar masses in order to have this variable, the time, that can link the evolution of stars in galaxies to the formation of galaxies themselves. So in this approach, unlike the previous one, the weights that we associate to the various locations in the HR diagram, which you see here in a cartoon phase, in a cartoon depiction, but it is quite physical, and I will comment on this immediately, are actually real weight by energy and time scales according to stellar evolution. Alvio Renzini, who is featured in the middle, who worked with Beatrice Tinsley at the same time, translated and formalized this equivalence into something called the fuel consumption theorem, where indeed the assertion is made that every contribution for stars in luminous phases post the core hydrogen burning must be proportional to the amount of nuclear fuel that is at disposal in these phases. I am a student of Alvio Renzini, and therefore my models are developed within the framework of the fuel consumption. And I think I will say only this because the fuel consumption itself and its application would deserve a talk in itself. But I need to stress this difference in order to acknowledge another main player in the population synthesis model for galaxies, which is in fact Gustavo Brusual, that you see here in the right picture, which model were started to be calculated and made published as early as 1983, so in the same time as the others, but where a different approach was taken, and namely an integration over isochrones that are combination of stellar tracks at a given time for all ages and all chemical composition. So it's very illustrative and interesting, the discussion about the two methods, but as I said, I will leave it. By studying the evolution of stars in this theoretical population, it came out that in fact the evolution of an ensemble of stars encompasses three main phases, and I would like to stress this from the beginning because we will see them later also. Populations that are younger than 100 million years have essentially one post-main sequence phase that is highly populated, which is the core helium burning phase of these massive stars, produce a lot of light. In slightly older population that we can set about 1 billion years of age, instead, the main post-main sequence phase dominating the bolometric light is the so-called asymptotic giant branch. We'll come back a bit on this later. And then finally, population that are a bit older than this 1 billion year that we used to call old. This definition may change from paper to paper, but that's not very important. I think this is the more robust because it is associated to something energetics. See as the main source of energy, the red giant branch. So this plot is actually based on real models. Now, in order to understand the core of the models that are in fact the center to derive any type of galaxy evolution conclusions that you find in the literature, let us examine briefly what are the model input physics. So the first things we need is a description, a quantitative description of the energy emission per stellar mass, which is just erg. We also need to know for how long this energy is emitted. So we need this time scale T, and in fact, the fuel consumption combine these two variables. There are phases in the HR diagram that are very luminous, especially giant phases, but whose time scale is quite short. So they will entail an increase in luminosity in the galaxy hosting these phases, but just for a short time. After you fix the energetics, you need to have a distribution function of energy per wavelength. And this is what we said is a stellar spectra, which we will see and we'll talk about better in a minute. Finally, one needs a distribution function to distribute the stars in mass beams. So answer the question, how many stars with mass like the sun are formed in your stellar generation? How many with very low masses? How many at high masses? Additionally, in certain type of models like mine, we also assume a distribution of remnant masses. As we know, stars live for certain time scales that is theoretically predicted for then leaving massive remnants in form of white dwarf, neutron stars, or black holes. And therefore, one needs to have the type of mass associated to the initial mass. And this is what I call the for remnant mass distribution. Now, there are colleagues who also include other type of physics in population models, which I call the extras, with all respect that I have for these quantities. And these are the fraction of stars that are actually in binaries, emission lines due to surrounding gas, especially in young population and nebula continuum. Now, I put it extras because they do not stem really from stellar evolution theory, but they are either assumed like the fraction of binaries or empirically set from observation like the Michelin nebula continuum. However, they are becoming very popular due to the fact that we observe galaxies at a higher and higher redshift. So let us briefly go through the main input physics of the models, as I just mentioned. Energy at time scale come from stellar evolutionary tracks, which you see here depicted in a theoretical luminosity versus effective temperature. This is a plot of quite nearly 20 years ago, but it is in fact the same situation as of now. There is a certain discrepancy in stellar tracks calculated with different input physics, especially for what the red giant branches are concerned. And this there is a detachment, so different temperature luminosity distribution at supersolar metallicity, but also at very low metallicities, which go in fact in opposite direction. Excuse me. And I'm showing here tracks for a wide range of schools. So what are the actual physics that we need to improve in there? And they go on cascade directly on our knowledge of galaxy. The extent of the core convective overshooting, which actually drives the luminosity, especially of stars that are in fact exhausting hydrogen in the core, the mixing length, which is assumed in envelope, and that has a direct consequence on the red giant branch temperature distribution, and the equation of state if you are interested in very low masses. The stellar mass distribution is actually a very trendy topic nowadays, since the address by certain colleagues that possibly the initial mass function as we know it and has been measured in the Milky Way may actually vary with galaxy masses, being progressively bottom heavy and therefore dominated by low mass stars, the bigger the galaxies, the most massive the galaxies. I will leave this important topic in this review talk, but I just wanted to say that from the point of view of the model, the initial mass function is merely an input, which we modeler can vary really at our leisure. But let's go to the stellar spectra, which are actually the critical ingredient for comparing with observation, for deriving redshift, for deriving chemical composition. There are obviously two possibilities, and modelers like myself have explored both. To adopt a full theoretical framework of model spectra from atmosphere, from model atmosphere, and they have, and these two references are among the most widely used, but actually giving a talk in Brazil, I should really mention the paper by Paula Coelho and collaborator, which is also inserted in this type of model atmosphere. These spectra have an arbitrary resolution and wavelength extension, coverage, any stellar parameter, and they are very flexible because they are built in the computer. The problem is some line lists may indeed suffer from accuracy, and Coelho et al. Pointed out inaccuracies at the Balmer lines, for example. I'm showing here something that related to a topic of discussion nowadays, but it's just an example, and it is the spectral region of sodium. And what I'm showing in the bottom panel, I show a dwarf star with low temperature, and in the upper panel, a giant star also with low temperature. And you see that the dwarf, the observed dwarf, which is the black line, is quite well depicted by a theoretical model from one of these papers. This I would rank as a good comparison. The giant, on the other hand, is missing a lot of titanium absorption, which will alter the continuum. You see here in this black line that are not fit by the models. So this is just an example. People have realized this well before me, and there are also schools in Brazil. I have a paper in mind by Claudia Maraston, who has actually try to build what it is empirical spectra. So instead of resorting to the theoretical spectra for model atmosphere, these people have tried to construct spectra based on actual real stars. I'm going to show the effort in which I've been involved directly, which also has the feature of being certainly the largest stellar library that has ever been published, and probably been published for a while. And the reason why it's so large is that the library was collected by using free time in the Sloan Digital Sky Survey, Apogee, and Sloan 3 experiment, Sloan 4, excuse me, experiment. So we call it MASTER, which means Manga Stellar Library. The effort was led by Renbin Yang, and here I show you a gallery of really beautiful spectra, from hot spectra to very cold spectra. They are shown as flux, of course, over a wavelength range. So what are the virtues of our library? Well, first of all, as I said, it contains 60,000 spectra for 25,000 unique stars. The previous state-of-art effort, the Miles, contained 900 spectra. The current tech shooter that I should mention, even less than that. So I will show you what it means to deal with so many spectra, but one of the advantages is that you can actually maximize the signal to noise, and also in principle, which is written here, obtain a wider coverage of stellar parameters, including some exotic location, exotic in the sense that they have been less sampled in previous effort, which included the bottom of the main sequence, carbon stars, and also hot spectra. Plus, actually, a big advantage, I think, is that these spectra have been taken with the same instrument with which the body of the Sloan galaxy spectra has been taken. So this means one has the hope that all the instrumental effects that affect the galaxy spectra will also affect the population model spectra based in this library the same way, which should facilitate the comparison to data. the wavelength range is relatively large for being taken with one instrument. So you don't need to normalize or link in between, but this was a continuum in the Sloan 4 spectrograph. Plus, because we have so many spectra, the signal to noise of individual spectra is really high. Here I say larger than 50, but in reality is well above 100. Now, the first things that you need, however, to take care, collecting so many empirical spectra has no utility in a theoretical population model if one is not able to give identity card to all of these spectra, namely devise effective temperature, surface gravity, and chemical composition for all the spectra, because otherwise we would not know to which stellar phase, which are here shown in blue and red, theoretically, we should associate a certain type of emission. There have been many efforts within MASTA, but we led actually the effort for devising this so-called stellar parameter. So the main parameters of really your star that produce that emission. And that was led by our PhD student, Louis Hill, in a series of papers. And so what we have done, which is for those of you interested in deriving stellar parameter, is quite interesting because there are two approaches, and usually for deriving stellar parameter, one take a very small wavelength portion of a spectrum, but at very high resolution. Instead, what we have been doing was to do full spectral fitting of models on the whole extension of MASTA. This is probably the first time this is done. Hopefully it's good, but we wanted to mimic already how we actually apply this spectra then to galaxies by fitting the spectra in each detail. And so you see here a gallery of accurate stellar spectra. And especially, this is all in the paper, but this I wanted to show because this is really a dwarf star, cold dwarf with high metallicity. And then you see all these bands, including a flare that, of course, we don't need to fix it. So in our lab, we have the largest number of dwarfs. So in principle, we can cover them in sequence down to the bottom. The other peculiar spectra that we have are carbon stars. Carbon stars is a species developing during the thermal pulsing on the asymptotic giant branch. So it's shortly before the star will get rid of the envelope and evolve as a white dwarf. But as you see from this miniature diagram that I put here, carbon stars are effectively super luminous. They are the most luminous before the star become a remnant, and therefore they are held to be quite fundamental in featuring the light of galaxies. We do have only a small range that is interesting for these very cold stars, but you can immediately recognize the broad CN bands that Miriani Pastoriza, another well-known Brazilian astronomer, has used in the past together with Rogerio Riffel. So, all in all, now I can present you this model so that we can discuss how they vary in age and metallicity. So in this short movie, you will see this is the age parameter. The youngest age is about 3 millions of years. The luminosity, of course, is normalized to solar units and will change according. The different colors indicate different chemical composition. And now I try to activate the movie. It works. At some point, you will see a bump here. See, this pronounced bump is due to red supergiants in young population, something that will be important at higher redshift. And then the population evolved. We are already 3 billion years, 7 billion years. You see another thing, at the aging of the population, the beauty of the metallicity really opens up. This is well known, and this is also giving us some problem because it's called age metallicity degeneracy. However, this is due to the fact that the temperature of the stars are suitable to open up most absorption lines. So models, of course, are public. As for many other authors, you can look them there, and we're about publishing the next round. Now, it is important in a talk of this kind where I explain the core of the model, just examine the influence of these evolutionary phases in making up the integrated spectral energy distribution. An exercise that with the fuel consumption we can do very well because we calculate the energetic phase by phase. So as an example, if I consider a model of 5 billion years of solar metallicity, and the black line is the integrated spectra, I will have the contribution of the main sequence run as it is shown, the blue line. The subgiant branch is very similar in temperature, obviously, as expected, but with less fuel consumption. The red giant branch has quite a substantial contribution to the actual light in this already old stellar population, but with a peak towards redder wavelength, as we know, because it is a red phase. The horizontal branch, or better said, the core helium burning is as an intermediate effect in this population, and then the early asymptotic giant branch gives a contribution peak to the red, but it is very small in fuel consumption at these stages. This is just an illustration, but in principle, this open up exists for all the phases, and they allow you actually to really check the calculation between models and models and to understand them. Now, with MASTA, we have been able, in fact, I claim, to cover the HR diagram extremely well. And you see here the latest that we publish contain temperature as high as 30,000 and down to 3,000. This is a plot where we plot the effective temperature and the gravity of the star, color-coded by chemical composition. What it was nice to see is that we can, in principle, model a wide range of ages. Here we see isochrones from the Padova group, just overlaid for age of 10 billion year and a very metal-poor population. 10 billion year, but a metal-rich population is the red line, which goes up to this extremely red giant type of stars, but also a population as young as 10 million year, which develop a red supergiant phase, which is the green line that nicely go to the stars at this high temperature. In the latest paper, we have also tried the let's say the challenge of determining detailed abundance ratio from this medium resolution spectra without invoking high resolution. And so this is a plot of the alpha over iron, essentially. So the ratio between iron and alpha elements of all the stars as a function of iron abundances. Those of you who are knowledgeable in chemical composition will notice the well-known pattern in the Milky Way, that the amount of alpha element increase at decreasing total metallicity. I don't want to say any more on this. These are just tools to make the models better. So with this type of new and massive input, we have in fact now models that are fully empirical, that goes down to very young ages. And we will see how proficuous they will be for the analysis of galaxies. But let me now take a little break before I show you the application and just go over the progress that have happened over the past 20 years in stellar population model, in order to give credits also to colleagues. And I have a brief bullet point that you can look afterwards, in which the really new physics that has been put through, the effect of these pulsating phases during the asymptotic giant branch, which has had still discussed an impact on the properties of high-redshift galaxies. And the Brazilian colleagues have actually helped a lot using these models. And then this plot that just showed you the effect of including carbon stars in the models is to enhance and make visible certain molecules that only develop during this phase. At the same time, we also studied how to include detailed element abundance ratio in models, which turn out to be crucial to determine the formation epoch of the most massive galaxies in the universe. In this series of paper, this approach has also been taken by Charlie Conroy in quite a similar way. And this was the plot that showed to the world that in fact galaxies, here written as ellipticals, are not solar scaled like the disk of the Milky Way. Rather, they are more consistent with an announcement of a factor of 2, so plus 0.3 in alpha elements, which directly connect with their formation epoch. And you can invite a colleague to give you a talk on that. It's very nice. High spectral resolution was actually pioneered a bit by Bruswell and Charlot 2003. Vasdekis 2010, our paper 2011, and then the paper I show you here. And this means that you can reach incredibly high resolution. Here I show you something that is theoretical rather than empirical, that you still need for population that are just 1 million years old. But the resolution is 10,000. For calculating this model, I have actually used a high resolution version of the Kuros libraries by Rodriguez Merinos. The ultraviolet spectrum is, again, it would deserve an own talk, is something very interesting because it may contain either star formation or all the stars. Klaus Leiterer explored this a lot for star formation, and in these two papers, instead, we have explored what happens if you have this hot but old stars in your population, which are, for example, the UV upturn in elliptical galaxy. Excuse me. And in this plot you see here, you see the ultraviolet in wavelengths as a function of flux, how actually the models can vary, just varying the parameter of the temperature of these hot phases. Finally, effort that of which I have no merit at all, the inclusion of binary stars, and especially this paper by Eldridge and Stanway has tried to make include is called bypass, and this is one of the plot comparing with my models. Of course, the models have to assume some parameters, not only the binary fraction, but also their separation. I have not done that, but I would like to mention to you they exist in the literature. Now, it's beautiful to calculate theoretical model, but how do we actually know that the model gives you physical properties that are sound? So, our approach was to test the model with nearby globular cluster. Globular cluster are compact ensemble of stars that have the nice and convenient feature of being coeval and chemically homogeneous. And they are coeval in spite of subpopulation that have been detected in the past few years that are really minimal. They are still simpler than galaxies, I say in advance. So in principle, if you have the spectrum of a globular cluster, that you know the age from the resolved color magnitude diagram, and for this exercise you only want nearby a globular cluster, you can in fact derive ages and metallicity independent on the model, and then constrain whether the model is giving you the right answer. And so in this paper 2020, we have done this exercise with our latest models, down to very young ages as young as 20 million years. And so at the end, you can get a global assessment, appraisal of your model, ignore these acronyms, but essentially we could demonstrate that with a certain class of models, we can get the age as good as 9% and the metallicity around 10%. Now, if it was like this for galaxies, we all would be actually very happy. Now, and the organizer should stop me if I'm going over time. I'm conscious that we started a little later, but still, I will try to show you some key application, which is mostly the interpretation of observational data and the prediction for galaxy spectra. So when you have your model, the temptation is to fit it to spectra. That's why we calculate model, which is great. You need a fitting code. There are many in the literature. You have Starlight in Brazil. We have developed our own code called Firefly. And so here we use this one, and essentially you apply to galaxies and you get these beautiful fits. In fact, the models can get you down to fantastic fit, to be honest with you, in exception except in a few cases, that's not difficult. But at the end, you get exactly age and metallicity, and you start to think about galaxy evolution. With the new model, we go up to 1 micron, while with models of previous generation, those models stopped here. So I will briefly show you what is the impact of this wavelength extension, if I can change. And I would like to acknowledge Justus Neumann, Dr. Justus Neumann, who has published the whole value-added catalog, which has been called Portsmouth, where we have applied our models, not only the last one, but also previous one that stopped around the 7,200. Why is this interesting? Because not every spectrograph, I see some lines, I hope it was not me. Well, not every telescope can actually get you the whole extension of the spectrum. So it is important to understand how certain properties actually depend on the extension of data that you fit, so that you can actually transport the same knowledge to other experiments. Then you get these beautiful maps. And what we have included, that is quite a novelty, also the maps of dark remnants, white dwarf and neutron stars and black holes resolved for all these galaxies. As I mentioned, and I think I will be able to go nicely to the end of the talk with just a couple of minutes of overtime. The galaxy evolution that you derive depend on the model, because it is with the model that you derive the main physical property of the galaxies. Like in the Heisenberg principle, you actually act on making your galaxy by putting a model on the spectra and getting out the properties. In reality, the offset are in most cases not significant, but they are interesting. And I would like just to point to Justus' paper to show that we have compared age, chemical composition, and also mass density for a range of calculation existing in the literature. Now, and this is the last topic I would like to address, stellar population models are also a critical ingredient for making galaxies in a cosmological model. This is a review by Carlton Ball that shows you all the steps that you need to take after you have fixed your cosmological model and your dark matter merger tree, if you assume a cold dark matter cosmo web, in order to make actual galaxies. And one of the ingredients is a stellar population model. And people have done this. We started actually 15 years ago to point out, and we are only at the infancy, how important is actually this ingredient in the comparison, and also derivation that you can have on the larger cosmological setup of the universe. But just to stay on time and to also acknowledge the work of our student Lorenza, I would like to show the latest effort, which is to make high-resolution spectra of galaxies from cosmological hydrosimulation. We have used the Illustris TNG, and that's why we call this effort IMANGA. These are actually galaxies in the Illustris, not in the real universe, but in the simulation. And what we have done, we have included this resolved spectra, model spectra based on 60,000 empirical spectra, and we have created the mock galaxy spectrum, which we hope will be the closest thing to an observation. And this will be useful to really pin down how galaxy evolution proceeds in a virtual universe and in the real universe. And we have the papers already accepted, and the catalog of these mocks, which can be adapted to many other type of experiments, is available. And here we just show you what we have been studying at the resolved, the gradient in age and metallicity, but you can take your wished galaxy property to pin down in the mocks and in the real data and see how well they compare. They did compare very well for these two galaxies, but we have 10,000 in the mock. We will have to see how we do. So I'm happy to close my talk with a very little summary. I hope I showed you that by 2022, we have most physical effects, including in model, not all of them, but most of them. And I also showed you that we need to test our model with nearby simple solar system first before trying to match them to complicated galaxies in which a lot of degeneracy take place. I told you about our effort in having tens of thousands empirical spectra as ingredient for the model. We hope we may be able to solve a few open issue in galaxy evolution, but this is not all. And one topic that is highly interesting to me is to try to improve more and more galaxy formation models in order to have compelling answers on the cosmology in the universe. Thank you very much for your attention.
Thank you so much, Dr. Maraston, for the very interesting talk. We now have time for questions from the audience. You can raise your hand and I'll call on you, or you can type in the chat also. Okay, go ahead, Anna.
Hi, Claudia. Thanks for the talk.
Fantastic. You come from a fantastic location, it seems to me.
No.
Hi, Anna.
I was wondering if the iManga, what redshifts do you have the spectra available? Just for redshift 0 or up to all what's available in Illustris TNG 50?
That is a very, very nice question, Anna. So it's called manga because initially we have extracted some sample to mimic the feature of the manga survey, and that gives you a small redshift range around redshift 0. But as you can imagine, because our latest model go down to 3 million years, we want actually to extend the construction of MOX to high redshift. And in fact, there is another student that will do that. So feel free to get in touch anytime. It is a very good question.
Go ahead, Reinaldo.
Hello, Claudia. Thanks
Hello.
for the excellent talk.
Oh, thank you very much.
I'm not an expert on this subject, but I have learned a lot about it now. Well,
oh, this is so nice.
well, I have a question about the input parameters of the model. Also as from a cosmological perspective. Can time scale and stellar density be directly related to a specific redshift? I mean, is there an explicit redshift related to these parameters? Or so maybe, are these values chosen from a cosmological snapshot, let's say?
No, this is, no. So the time scale of the stars is in principle independent from cosmology. It's not, I stopped at the plot which I should not stop because you don't need that. Let me go back here to the stellar evolution, essentially. So stellar evolution is detached from cosmology in the sense that the time scale intrinsic to that is related to the burning, to the nuclear burning. Okay, so in principle, you can have any age at any redshift and at any location in space. Okay, there is the knowledge, and I think it is. I mean, so theoretically, you can do everything. For example, in my model for high redshift galaxy, where I calculate K correction and evolutionary correction, I do not assume a formation pathway for galaxies, which would associate, as you were saying, timescale and redshift univocally. For example, you can assume the galaxy form a redshift 5 and then evolve, then you need to follow that path.
Oh, good. That's the point I was thinking about. Yeah. Okay.
Exactly. But to my perception, is better to have a free table in which at every redshift, you can have every time. Then you can impose your favorite cosmology, which will give you a look back time, which perhaps you don't want to violate. So you do not want to have galaxies as old as 10 billion years, redshift 15 in a lambda CDM universe. But having the table so free allows you to play with other cosmologies, which I think is a good advantage. So to answer your question, some authors associate uniquely timescale to redshift. These are the table by Brusual and Chalot, but for example, I let it free instead, exactly to explore cosmology.
Okay, thank you very much. I have another question, if you allowed me, just a technical one. It was not clear to me if you use any metrics to validate the model when comparing observed spectra with synthetic ones, or it's just the overlap of both, like in iManga you have shown.
Yes,
because,
so okay.
Yeah, I'm asking you on that issue because we have some recent techniques to make a very fine comparison, okay, between supernova type 1 spectra. So maybe it would be useful to validate also this kind of spectra, okay?
I think this is very interesting, and I would love that you send me a reference for that. The metric we use is essentially when you perform this fit. Let us first look at the basis. You will derive, you see here, I write the best fit model that give you exactly this age, 4.57, metallicity 0.26.
Oh, I see, okay.
Exactly. In case of globular cluster, you have age and metallicity from resolved studies that are independent of the models. And then essentially you compare them. And then you get histogram like this, in which I put on the x-axis the difference in the age derived from the models, and the age determined from the resolved stars, which you can only do in the Milky Way. And the closer they are to zero, the better your model will behave. And I can tell you from experience, a 9% offset is quite good in the field. When you have galaxies, when you have galaxies instead, you can't do that because galaxies are a complex stellar generation. What people usually use for galaxies is the best fit, which sometimes, you know, especially if you use manipulation to your software, you can get the best fit because you're stretching the spectrum. Now we don't do that. So essentially the best fit effectively will give us some indication, right? Whether we get the model or the blue. So for the globular cluster, I think we have a robust metric. For the galaxy, less, because otherwise, unless we make the prior that we know when galaxy form and evolve, which exactly we don't want to do because we want to use the model to derive the properties.
That's right. Okay. Okay. Thank you very much.
Thank you for these interesting questions.
Thank you.
Anna, do you have another question?
Yes, I have one more. So Claudia, about the globular clusters, I think you showed only the optical, that you're using only optical data, right? For the galactic GCs. Would it be interesting to have near infrared and UV spectra for a wide range of GC property data?
So Anna, here we only use the same range as this data by Asher et al. And the range of the master-based model.
Okay.
And only for this reason we have this. For old cluster, well, I mean, they're not too old, they're actually pretty young. But this is what we have. But the near infrared, as you know, also probably from my past paper, it's fantastic to fit. We don't have near infrared extension within this pot of data, but if they would exist in the literature, please do send me an email. They certainly exist and I'm an ignorant, so apologies. But to that, I would need also resolved near infrared spectra, which at the moment are less developed than the optical. I have a version of my spectra based on the IRTF set of spectra and some other spectra from Brazil, actually. But the coverage of stellar phases is not as wide as in these, which does not mean that I should not challenge the model to try to fit them and maybe get a bad fit. Regarding the UV is a bit, it is useful for super young clusters. which we don't have many calibrators, because these are the youngest I could find in the LMC, which are relaxed in a sense, right? That are 20 million years, that you have all the phases. The UV gives you the instantaneous shot of star formation. So it's good for galaxies to just see what's going on or to have the UV upturn. For globular clusters, well, at high redshift, they will be bright in the UV. Let's say locally, the fit I do is mostly where the models match exactly the data. I have no prejudice on other wavelength range, and I would be delighted to push the model even more.
Because we're collecting data for GCs in galaxies in the near infrared spectra with SOAR, but for nearby systems, not Milky Way, but they're integrated as the Usher ones. Yeah,
that would be in any case extremely interesting, Anna. So please do get in touch.
Okay.
Thank you.
Do we have any more questions from the audience?
No, I just want to say hello to Claudia.
Hi, how are you?
I'm fine, and you?
I'm good, and yeah, we haven't seen each other in ages.
About 20 years or something like that.
Oh my God. Okay, well, yeah, actually 10 years. 10 years ago, I was in Brazil.
But did we meet? I'm not sure. Did
I
we?
think so. Yeah, I think. Yeah. I went also. I was in Porto Alegre, but then I flew to Rio. So I think.
Well, it's better than 20 years.
It's better than 20 years, but still such a long time. I think we need to catch up.
Definitely.
Thank you.
Thanks for coming.
Of course, my pleasure.
Okay, I actually have a question regarding I've been working mostly recently I've been working on forward modeling for SPS, parameter estimation. Do you have any particular comments on that, like how this compares to the template fitting, and maybe if we can benefit from what you're doing to make our parameter estimation?
Yeah, no, very nice question. This iManga actually have been then placed into a forward modeling approach by including all the observational things, exactly as in the manga. Effectively, initially the input was to associate the theoretical population model spectra to the mass bins in the TNG, but then they have been added by a large amount of observational effects. So actually we have at the end, which I showed just like one case here, is a mock, which we call it mock, but it is a forward modeled galaxy model. So I completely agree with your approach, especially in this type of surveys in which you do have a peculiarity of your instrument, of your signal to noise, the PSF, the transmission for a lot of stuff. I encourage you to look at this paper. The first one is published. We have bit by bit added, and then we perform the fitting, but essentially, as you probably do in your approach yourself, treating the model galaxy as if they were observed galaxies. Exactly, and fitting them, in this case, with our code Firefly, but with the same routine as we would fit the data. And this is what this plot would like to show. The yellow line are the intrinsic quantity. For example, in this, what is this? Age versus effective radius within a galaxy, because these are IFU, but you can do it in every range. The yellow is the intrinsic, and the black is what we derived by fitting the mock forward modeled galaxies with the same routine and the same set of templates. So I'm fond of forward modeling because if you add the observational, all the observational effect, in principle, you are less prone to get fooled by some degeneracies that in fact are there. And you know, moreover, we also use the same stellar population models with the same instruments. So we hope, I like the strategy, to be honest with you. There is no discrepancy.
Okay, thank you.
No
Anna, do you have another question?
No, I just forgot to lower my hand.
Okay. Let me just quickly check on YouTube if there are questions in the chat. No, let me check the chat here. Okay. Okay, so if there are no more questions, we'll wrap this up. This presentation will be available on our website and on Linea's YouTube channel. Thank you everyone for attending, and a very special thanks to you, Dr. Maraston, for the great talk. Everyone have a great day, stay safe, and I hope to see you all again in our next webinar. Thank you.
And you too, and thank you very much for the invitation. And